Let's do an example. Suppose we have a set of data z1, y1 through z5, y5 as follows. z1 is given by 1, 3, z2 is given by 2, 4, z3 is given by 4, 1, z4 is 3, 1, and z5 is 4, 2, with y1, y2, and y3 equal to k0, which is 0. Okay, so the first 3 points are of class 0. And y4 equals to y5 equals k1, which is 1. So the last 2 points are of class 1. Apply logistic regression by doing the following. A. Find the log likelihood function L of beta. B. Apply iterative reweighted least squares to find estimates for beta 0, beta 1, and beta 2. C. Find the estimated probability function p hat of x, where p of x is the probability that y equals to 1 given x equals little x. D. Classify the new point 5, 0 using the estimated probability function. Okay, so for part A, the log likelihood function L of beta is given by this. And we have 5 data points, so big N is 5. And beta is beta 0, beta 1, beta 2. Zi prime is the column vector 1, Zi1, Zi2. Okay, so we have our data points. So we have the values for the Zi prime. So just plugging that in here, okay, for each of the 5 data points, we get this. Okay, so the first 3 terms, those are for the first 3 data points, and these 2 expressions are for the last 2 data points. Now for part B. In iterative reweighted least squares, we pick an initial value beta 0 and update beta t by this formula here, where z is given by this matrix, p is given by this column vector p of z1 through p of z5, w is given by this matrix p of z1 times 1 minus p of z1 dot 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 p of z5 times 1 minus p of z5. It's a diagonal matrix. And v is given by this. Recall that p of zi is given by this formula. We'll pick beta 0 to be 0 as the initial value. Then p is given by this, w is this diagonal matrix, and v, if we solve for v, we'll get this. Now, using all of this, we can solve for beta 1. So beta 1 is given by this, which is approximately negative 0.69, 0.48, negative 0.48. We update PWV and calculate beta 2. Okay, so beta 2 is approximately this. If we keep iterating, we get beta 3 and beta 4. Beta 5 and beta 6 are nearly the same as beta 4. Okay, so it looks like we get convergence. So beta t converges to this vector here. The estimates for beta 0, beta 1, and beta 2 are given by beta 0 hat, which is negative 1.05, beta 1 hat equals to 0.642, beta 2 hat is negative 0.642. Okay, that's what we got here from this vector. Now for part C, P hat of x is given by this, okay, where we have beta 0 hat, beta 1 hat, beta 2 hat. So we'll just plug in the values we got. Okay, P hat of x is given by this. Now for part D, P hat of 50 is given by 0.8966. Since there are only two classes, we classify x as of class 1 if P hat of x is bigger than 1/2. Therefore, we classify 50 as of class 1, okay, because this is bigger than 1/2. Note that setting beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2, setting that equal to 0, gives us a decision boundary that corresponds to the probability being 1/2. In this example, the decision boundary is given by this. And that's just the line x2 equals x1 minus 1.6. Here is what it looks like with the data points. So here's our line, x2 equals x1 minus 1.6, and our data points, the red triangles, and the two green squares. Okay, x2 being greater than x1 minus 1.6, that corresponds to the probability P hat of x being less than 1/2. So that's this region up here. x2 being less than x1 minus 1.6, that corresponds to the probability being greater than 1/2. So that's the region below the line. Okay, so any points here would be classified as 1, classified as of being of the class 1. Any point above this line will be classified as class 0.